Okay. Good morning. So announcements. There is the lab 3 deadline that is coming on Thursday, and also quiz 6. So a note about quiz 6. It's supposed to be super easy. I looked at the logs of those who have taken it. It was about 5 to 10 minutes so far. So due to the fact that we have a lab due on Thursday, this quiz is designed to be easy, and you shouldn't be spending much time on at least taking the quiz. Preparation for the quiz is a different topic. Okay. Yeah. Okay. So if there are no other questions, I actually want to see if I can do screen monitoring. Sorry about that. Let me see where my keyboard. Okay. Okay, now it's good. Okay. So, the only thing I have to do is now to oh, this is so messed up. Yep, sorry about that. Okay, this becomes my desktop. Send live. Okay. Okay, so I got that there is an echo. Is it still there, or is it resolved? Okay. So we were talking about real-time systems. So let's get back to it. Okay, I think I wasted a lot of time and it's not actually working. Let me disable this. Sorry about that. I wasted a lot of time off. Okay. Okay, so let me know again if there is echo. I hope it's resolved. That was a failed experiment. Okay, so in the last lecture, we talked about two main categories of scheduling. That one was online and one was offline. We said that offline is not of our interest because offline, basically you have to know your workloads and then you just come up with whatever schedule you want. You put it in a table, and then when the system starts running, you know what's going to happen, right? You have written everything. So that's offline. We put it aside. Now, in the class of online algorithms and online scheduling policies, there are three main categories. One static, second one dynamic, and then the third one is fully dynamic. So just to remind everybody about periodic tasks. So if you have, let's say you have a task that is periodic with let's say period of 17 and worst case execution time of 10. What does this mean? It means that this task, if this is time, starting from 0. So every 17 time slots, so after 17 time units, a new job from this task comes. So at this point, at time 0, the first job from this task comes. And at some point, you're going to schedule it. You could schedule it at the moment it comes. You could schedule it somewhere else. You could schedule like 1 unit of it here, and then few units of it here, and then later on some other units here. But in total, the execution time of this job, the first job of this task, would be 10 units. Then at time 16, the second one comes, second job. And then you have time until time 32 to run it. I think I made a mistake. It should be 17 and then 34. Yeah, because it's 17. So that's basically what it means. Now, is there anything to clean? Okay, so you have periodic tasks that basically are represented by set of jobs. You have aperiodic tasks, so it's just one task. So for aperiodic and sporadic tasks, you have this one-to-one. So each task is one job. But for periodic tasks, then each task is a set of jobs that periodically will arrive at your system. this is basically what we said. So there's periodic tasks, aperiodic tasks, sporadic tasks. As I said, aperiodic and sporadic, you have one-to-one. Each task has one job. But for periodic tasks, you have one task that has a set of jobs. Now, although I have to mention, so you might see somewhere that this aperiodic task also might have jobs. So they might say one aperiodic task or one sporadic task could be a set of jobs, but then those jobs don't have a period. They just come at some point. But that's not common. Usually there is one aperiodic task, which comes and goes, and that's it. And then the next one that comes is another task, right? So you don't put them all in one group. Whereas here, each one of these arrivals, we call them jobs, and the entire set becomes a task. Now, with a static scheduling, we give each task, and if it is a periodic task, all the jobs associated to this task, all of them will have a set priority, and that priority doesn't change over time. With dynamic scheduling, now the unit of assigning priority becomes jobs. So now we assign priority to jobs, and we say that if you set a priority to a job, that priority is not going to change going forward in time. And then finally, fully dynamic scheduling, again, the unit of assignment is basically jobs. However, your priority might change. Now, this hopefully becomes clear when I give you examples of these three scheduling policies. We're going to talk about them, but this is just high level. Now, here's something that is going to get a little bit messy in terms of definitions. So we say a Schedule S, a scheduling policy, or a Schedule S. No, let's talk about a schedule. If I give you a schedule of tasks, tell you, you know, start this task at this time, start this task at this time, and so on and so forth. That schedule is feasible if all the tasks that I have in my system, they all meet their deadlines. So if I give you a schedule, and in that schedule one task misses its deadline, then that schedule is not feasible. Let's say I have one task that has a deadline of 6, but the schedule I give you, that task finishes at time 8. So that means that this task is missing its deadline, so it's not feasible. Now, fix a task set, a workload, just fix some number of tasks that you have. And then focus on a scheduling policy class. So you have 3 classes of scheduling policies: a static, dynamic, fully dynamic. Now, a task set T is a schedulable under that class if there exists a scheduling algorithm in that class that produces a feasible schedule for that task set. So I say it again. So in this, there are 3 elements. One is a set of tasks. So fix a set of tasks. Then the second element is fix a class of a scheduling, a static, dynamic, or fully dynamic. Or even go further, say online schedulers, right? That's a bigger class. So set a class. Now, in this class of scheduling policies, there are so many different algorithms. So so now we say this task set is a schedulable under this class if there exists at least one scheduling policy that can schedule this task set in a feasible way, meaning that it can schedule all the tasks so that they meet their deadline. And if that's true, then we say this task set is a schedulable under this class. it might not be. So you might find a task set that no scheduling policy under, let's say, a static scheduling can meet every task. It can make every task meet its deadline. So at least one or two tasks would miss their deadlines. Again, we'll see examples of this. And finally, we say a scheduling algorithm or a scheduling policy A is optimal with respect to its class. So it's from a class. So any algorithm is from a class. Any algorithm is either static or dynamic or fully dynamic. So we say that a scheduling policy is optimal in that class if it produces feasible schedules for any schedulable task in that class. So if you give me a set of tasks and there exists a scheduling policy in this class that can schedule that, then I can also schedule it. So I'm as good as any other scheduling policy in my class. Then I become optimal, right? It's like the top student in a class. If anybody else can do this, then I can do it too. Then I'm optimal. Okay, now that's definition. We'll come back to it. If you didn't understand it fully, it's fine. I will come back to it. Now, let's just talk about why general purpose schedulers fail in real-time systems. This is one task set. I have 3 tasks. All of them are periodic. The task 1 has a period of 2, task 2 has a period of 5, and task 3 has a period of 10. And these are the worst case execution times of each task. So task 1, execution time 1, task 2, execution time 1, and task 3, execution time 3. Let's see how round robin, which we saw, how does it do in scheduling this set of tasks. What happens first? So first, let's mark the times that a new job from each one of these tasks come, right? This has a deadline of 10, so at time 0, at time 10, this has 5, so 0, 5, and 10. This has 2, so 0, 2, 4, 6, 8, and 10. Now, let's do round robin, assuming that T1 is the first one in the queue, T2 is the second one, and T3 is the third one. Okay, so we're going to give one time unit to T1. And by doing this, actually T1 is done in this period because it got one unit, and that's all it needed in this period. So T1 is done. Then we give 1 unit to T2. We move on to T3. T3 gets 1 unit. Now we go back to T1. So T1 now has a new job. So we can give it actually 1 unit here. It gets 1 unit. And now 2 jobs of task 1 are done. We go to T2. So here T2 doesn't need anything because in this period, it only needed 1. So every 5 time units, I need only 1. So I'm done. I don't need anything. So I can move on to T3. So T3 now gets 1 unit. Now we're going to go back to T1. So T1 again gets a unit. Now this time we're going to go to T2, and T2 now has a new job. So we can actually give it to him. So it gets 1 unit. Now we move to T3. T3 gets a unit. Now T3 is also done. We're going to go back to T1 and see what happens. So what happens is in this period, T1 did not run any job. So this job that arrived here missed its deadline here. Just by a simple round robin, T1 here missed its deadline. So round robin does not guarantee any timeliness when it comes to jobs and tasks with deadline. Okay, now here comes the first real-time scheduling policy that I want to introduce. So the first one we're going to see is a static scheduling. So rate monotonic is a scheduling policy that assumes that all the tasks in your system are periodic and they're all independent from each other. So there is no dependencies between the tasks. And it assumes that you know the execution time of your tasks. So that worst case execution time, we assume that we know it's exact, right? You can actually relax some of these. Then here is how it works. It's a static online scheduling policy. So it's going to assign priorities to tasks, not to jobs, to tasks. How does it do? It gives higher priority to any task that has shorter periods. So it basically sorts tasks based on their period, and it assigns tasks with lower period higher priorities. Simple. Now, one thing that I'm not actually going to prove, you're going to get it, take it from me, is that RM, rate monotonic, is optimal with respect to static schedulers. Now let's revisit this. What does it mean? What does this sentence mean? It means that if, so give me a test, a set of tasks. So let's set a set of tasks, like the previous example that we had 3 tasks. Give me a set of tasks with their characteristics. Now, if there exists any static scheduling policy that can produce a feasible schedule for that task set, then you can prove that rate monotonic can do it too. That's basically what it means. It means that if for a particular task set, there exists any scheduling in the class of static schedulers that can schedule that task set in a feasible way, then you can be assured that rate monotonic also can do it. Basically, rate monotonic is the top student in this class. Now let's look at it. Let's run an example with rate monotonic. So here I fixed this task set, which is the same as the one that we saw before. Now look at the periods. So this one has a period of 2, this one has a period of 5, this one has a period of 10. So according to rate monotonic, task 1's priority is more than task 2's priority, and task 2's priority is more than task 3's priority. So we fix this priority. This guy becomes our top priority, this guy becomes our medium priority, and this guy becomes the low priority task. Now, again, we mark the arrivals of each task's job. Now we start. Okay, at time 0, I have 3 arrivals. All of them are here. I give it to the high priority task. So the high priority job, which is a class of this. So a job of task 1 takes the CPU, and it's now done. So now time 2 comes, the second time unit. I don't have any job in task 1. I have a job from task 2 and task 3. Well, task 2 has a higher priority. It gets it. Now, here comes the interesting one. Now, in this point, task 1 has a new arrival, and this guy actually gets a higher priority compared to task 3. So we're going to give it to task 1. Now here it's done. Now there is no job from task 1. There is no job from task 2. So task 3 gets a chance to run. Again, at this point, task 1 comes. So it has a higher priority. It takes the CPU. At this point, this guy comes. It takes the CPU. Again, at this time, task 1 comes and has a higher priority. It takes the CPU. And again, we're in a situation where there is no job of task 1. There is no job of task 2. So we can safely give it to task 3. And you can actually run this. So what you can see here is we were able to schedule, to produce a feasible schedule for task 1, task 2, task 3 from time 0 to 10. Now, are we done? Yes, we are sort of done. Why? Because 10 is the least, what was it, least, it's the smallest, my brain doesn't work. But basically what it means is that 10, the number 10 counts all the, is a multiply of all the periods. So you can actually use this as a stamp and stamp this over time. So it just keeps repeating itself as you go, right? So starting from time 10, you can just, copy this here and continue. Okay, so for this particular task set, rate monotonic worked if it produced a feasible schedule. Now, can rate monotonic scheduling policy do that for every task set that we throw at it? Let's see. Here's another example. In this example, I have 3 tasks again. So 3, 5, 8. I got a question. If T1 and T2 had the same period and execution time, then T3 could starve forever, right? Yes, correct. No, wait. If T1 and T2 had the same period and execution time, not necessarily. You could assume that, let's say T1 and T2 had a period of 20 and execution time of 1. Oh, you mean, and it would be lower than task 1, but even that, you could find situations that it actually works. So we actually will talk about it, but I think one example that comes to my mind is, let's say task 1 and task 2 have period of 10 but execution time of 1, and task 2 has period of 20 but execution of 2, and this would still be feasible. So our M could still work it out. Time 1 and time 2 goes to T1 and T2, and then time 3 and 4 goes to T3. So you're done. It's you could put all the tasks there, and then it just repeats. So actually, we'll talk about a formula for this. But look at this example. So again, let's mark the arrivals. T1 is going to have higher priority than T2. So in this example, T2 needs 2 time slots to finish, and it gets it. Now again, T1 comes, so T1 gets 1. Now at this point, I can give it to T3, but then immediately afterwards, T2 comes, so T2 gets 1. And then here T1 comes, gets 1. We go back to T2. Now, what happens is now we want to come to T3, but we've already missed this task's deadline because it needed 2 time units on CPU, and it only got 1. So here it misses its deadline. So T3 missed its deadline. What does it exactly mean? It means that rate monotonic wasn't able to schedule this task set. So it failed to schedule this task set. Now, a lot of people worked on this problem. Under what circumstances does rate monotonic produce a feasible schedule? And what they came up with, and this is a theorem, is that for any n periodic tasks, you name it, so you come up with n periodic tasks, with known worst case execution time and known periods, so EI and PI for each one of them, then rate monotonic is guaranteed to produce a feasible schedule if this holds. So let's look at this formula. on the left-hand side, you have the summation of EI divided by PI. If you go back to the slides before and think about what EI divided by PI means, it was the utilization of the task. What that means is, if my task has jobs that arrive every 10 seconds, and each one of them needs 2 seconds of execution time, it means that my task is going to utilize 20% of the CPU, because every 10 seconds, I need to run for 2 seconds. So that means that I'm going to utilize the CPU by 20%. I'm going to get 20% of CPU time. Now, add up all the tasks that you have in your system. So that would be the utilization of your system. Now, for now, we're talking about the uniprocessor. So this shouldn't be more than 100%, because if it is more than 100%, then it's not even feasible. Like it cannot happen. You have only one CPU, and you can utilize it by 100%. If you sum up the utilization of your tasks, and it's more than 100%, then no scheduling can actually schedule your task. So it's hopeless to think about those situations. Now, let's say it's less than 100%. So this is the utilization of your task set, the total utilization. If it is less than n times 2 to the power of 1 over n minus 1, then it is guaranteed that rate monotonic can produce a feasible schedule. This, however, does not mean that if it is more than this number, rate monotonic cannot. If the total utilization is more than this number, then we don't know. Rate monotonic can or cannot, or might not produce a feasible schedule. We don't know. But if it is less, then we absolutely know that rate monotonic will produce a feasible schedule. Now, if you plot this, so if you plot this number, the right-hand side, n times 2 to 1 nth minus 1, for different number of n's. So on the x-axis, I have n. On the y-axis, I have the utilization, or the bound on the total utilization. You can see that as the number of tasks in my system increase, this bound goes down. So for, let's say, 124 tasks, you can have this guarantee if your total utilization is less than probably 68% or something. Now, again, as I mentioned, this condition does not say anything if this condition is not held, we don't know anything. So it might or might not work. Here is an example, right? In this example, if you add up the utilization, 1 over 3, 2 over 5, and 2 over 8, these are the utilization. So total utilization is 98%. And 98% is more than 78%. So this is not met. This inequality doesn't hold. However, this is the example that we saw, that rate monotonic was able to meet the deadlines in this one. Was it or wasn't it? Yeah, I think in this example, it wasn't, if I'm not mistaken. So yeah, in this example, it wasn't able. But you can come up with examples that the inequality doesn't hold, but you actually can schedule on the rate monotonic. Okay, so just to recap, we talked about rate monotonic. We talked about the feasibility of it. We also said that it's optimal for the class of static schedulers. So one thing I want to note is now it should be hopefully clear what static schedulers are. Because as you saw with rate monotonic, we just gave a priority to T1 and it wasn't changing over time. And every single job in T1 had the priority of T1. So T1 had a set priority and it didn't change. So we assigned priority to tasks, not to jobs, and it was not changing over time. And that basically means a static scheduling. Now you could do that differently, but with rate monotonic, you give higher priorities to tasks with shorter periods. Now let's move on and talk about the dynamic scheduling. So if you remember, in dynamic scheduling, we're going to assign priorities to jobs rather than tasks. Now, how does it work? So it's a EDF, or earliest deadline first. This is a scheduling policy that you will implement in Lab 4. So it assigns higher priorities to tasks that have earlier deadlines. So if I have two jobs. If I have two jobs, one of them has an earlier deadline, it gets higher priority compared to the other one. We'll see examples of this. Now, the current priority of tasks depends on how close their deadline is, right? So, and now you can see that because we're assigning priorities to jobs, then tasks priority is basically changing over time because each task has a different job over time, and each one of these jobs is going to get a priority. So it's as if the task's priority is changing. Now, the priority that we assign to jobs are not going to change. So if a job has a priority, its priority is fixed, which is basically related to its deadline. So because the deadline is not moving, so the priority is not moving either. And the cool thing about EDF is that EDF is optimal with regard to all online schedulers. So the class of schedulers that EDF is the top student is all the online schedulers. So all three categories of static, dynamic, and fully dynamic. Any online scheduling that you come up with, if they can produce a feasible schedule for a task set, then EDF can do it too. So EDF is very powerful when it comes to schedulability because it's optimal with regard to all online schedulers. Now let's look at EDF. Let's run an example here. We're going to actually look at the same example that we saw. I believe it's the same. It might not, but I think it is. So 3 tasks, deadlines, periods of 3, 5, and 8, and execution times of 1, 2, and 2. Now, let's run this example. At time 0, I have 3 jobs in my system, 1 job per task. I look at their deadlines. So this is the deadline of job 1 of task 1. This is the deadline of job 1 of task 2. And this is the deadline of job 1 of task 3. Which one has an earlier deadline? Well, this one. So I'm going to run T1's job. Now T1 is over. So job 1 of T1 is over. Now I have 2 jobs in my system. Which one has an earlier deadline? T2. So I will run T2. So T2 runs. Now at this time, a new job comes of T1. When is its deadline? The deadline is here. I still have a job of T3 where when is its deadline? Its deadline is here at time 8. So I'm comparing 8 and 6. Well, 6 is closer. So T1 gets job of T1 gets higher priority, it runs first. Now at this time I don't have any other jobs from T1 and T2, so I will run T3's job. Just one unit. Now look at this one, this is interesting. At this time, job 2 of task 2 comes. Now I have, at this time I have two jobs in my system. Job of task 3 and job of task 2. I look at their deadlines. The deadline of job of task 3 is 8. The deadline of job of task 2 is 10. Which one is earlier? Well, this one is earlier. So I actually continue running the job of task 3. Now, again, at this time, I get a new task, a new job. So now I'm comparing, I have two jobs in my system, one from T1 and one from T2. T1's job has an earlier deadline. I give it to T1. Then I move to T2. And this just continues. Okay, I'm not going to run the entire thing. It's easy to run, so do so by yourself. Let me see, I got a few questions. So is dynamic the same this? What? Is dynamic the same this as online? Can you ask this question again? I didn't get it. Okay, so there is no set of jobs that RM scheduling can do that EDF cannot do, correct? So if anything that RM can do, EDF can do as well, because EDF is the top student in the class of online schedulers. So any other scheduling policy that you can come up with that is online and can schedule a task set, that means that EDF also can schedule that task set, meaning that it can produce a feasible schedule for that task set. Okay, sorry, can you explain online schedulers and how they're different from other type of static schedulers? Oh, so online is, so I actually did this. So I said we have two on top of the list. There are two classes, online, offline. We said we're not going to care about offline. So let's put offline aside. Then we have online. Now in the class of online, we have three subclasses. We have a static, a dynamic, and fully dynamic. So all three of them are online. Now, hopefully that explains. So a static schedule is online. A dynamic schedule is online. A fully dynamic schedule is also online. Now, when I say EDF is optimal with regard to online schedulers, it means that any scheduling policy in any of these three subclasses, EDF can schedule if they can schedule too. Okay, what is the difference between dynamic scheduler, online scheduler, and dynamic online scheduler? Hopefully that explains what I just said, right? Because dynamic scheduler is an online scheduler. So online scheduling is a parent class, and then in the parent class you have all these three subclasses. So there is no set of jobs that okay, so why would you ever use RM? That's a great question. Why would you ever use RM if EDF can do it? Now, you can see here that implementing EDF is a lot harder than RM. In RM, it's easy, right? You can just look at the period of your tasks and assign them priority based on that. You don't really care about when their deadline is coming, and then each task doesn't have different deadlines, and so on and so forth. So EDF is the simplest one among the ones that we're going to talk today. It's very easy to implement, and in fact, in many systems, they prefer to do RM because of its simplicity, although it's not as powerful as EDF. So then, or anything other than EDF even. Yeah, so I think I explained that, hopefully. Okay. Now, here is the schedulability test for EDF, very similar to what we had with RM. This is the power of EDF that you can see here. It says that for any n periodic task with execution time EI and deadline of PI, then EDF is guaranteed to produce a feasible schedule if the sum of utilization, the total utilization, is less than 100%. So as long as sum of utilization, total utilization, is not more than 100%, EDF says, sure, I'll take it. I can schedule it, and it does. So this is how powerful it is. So just give me a task set that the total utilization is not more than 100%, because again, as I said, if it is more than 100%, well, you can't do anything because you have only one CPU and that produces 100% utilization. So if it is less than 100% or equal, then EDF says, yes, sure, I'll do it. Now, a system that has total utilization of more than 100%, we call it an overloaded system. Now, here comes the sort of downside, if you wish, of EDF. So when you have an overloaded system, then EDF is a little bit weird. Well, it cannot, first of all, it cannot schedule all tasks to meet their deadlines. It's impossible. But now the question is, does it do at least, you know, the best possible schedule, right? Meaning that, can it meet most of tasks? Now that we can't meet everybody's deadline, can we say that we're meeting the maximum number of tasks deadline? And the answer is no. So the moment your system becomes overloaded, you don't have any guarantee on how optimal you do, right? Because you could actually think about this. You can say, okay, my system is overloaded, so I'm going to miss someone's deadline. Now, can I guarantee that I meet like a majority of tasks deadline and just miss one or two? With EDF, you cannot say that. Here's an example. So here I have a system with 4 tasks. The deadlines are, the periods are 4, 5, 6, and 7. And if you calculate the total utilization, it's more than 100%, so it's going to miss its deadline. Now, what does EDF do? EDF looks at the first task with lowest deadline. That would be T1, because its deadline is 4. Everybody's deadline is 5, 6, and 7, which is coming in the future. So it first runs T1's job. So it runs for 3 time units. Now at this time, it wants to schedule another task. Well, it looks at the 3 other ones. And the deadline for T2 is the earliest that is coming. So it starts running T2, but soon at time 5, it misses T2. So T2 wanted 3 time units on the CPU before time 5. It only got 2, so it misses its deadline. So okay, I missed T2. Now I move on to another one. Which one I do? I pick T3. I start running T3, but then T3 also misses its deadline. Then I move on to T4, and then T4 also misses its deadline. So it basically cascades, as you can see here. I'm only able to run T1 under EDF. Now, is this the best I could do? Not really. So you could actually do better. Any of these 2 schedules are better. So if you do T1 and T3 or T1 and T4, you can see that you can meet their deadlines, and then you miss T2, in this case T2 and T4, and in this case T2 and T3. So, but at least you can guarantee that you meet T1 and T3's deadline, or T1 and T4. So that's the only, if you wish, of the downside of EDF. It doesn't really say much if you have an overloaded system. There is no guarantee that you can, maximize the number of tasks that meet their deadlines. Okay, let's move on to the last class of online schedulers, which was fully dynamic. So if you remember, with fully dynamic, we're going to assign priority to jobs, and a job's priority could actually change over time. And here it comes. So here is one example of such a scheduler. It's least-laxity-first scheduling policy, a mouthful. So to define this, I have to first define what laxity means, or I think another term that is used in the community is a slack. So what is a slack of a task? So I think it's well shown in a picture. Let's say that this is time. Let's say we're at time t, and the deadline of my task is time at d, sometime in future. This is the deadline. Then, assuming that I have e time units remained of my task to execute, or my job, then the laxity of my task is basically the slack I have. Let's say if I were to run my task right now at time t, it would take e time units, and then it would finish at t plus e. Now from t plus e until d, this is a slack. Now if you think about this a little bit carefully, you can see that this is slack. The more it is, the more flexibility I have. It basically means that this is how much time I have to schedule my task or my job, right? If this slack is 0, it means that I have to immediately schedule my task. Or if I don't, I will miss its deadline. Because if a slack is 0, it means that if I run it now, then t plus e becomes d. So if I run it now, I will exactly meet my deadline. And if I don't, and I wait another time unit, then I'm going to be missing my deadline. So this is slack. The more I have a slack, the more I can potentially delay executing my task, the more flexibility I have to schedule my task. Hopefully that makes sense. Now, least-laxity-first says, look at your jobs and tasks in the system, schedule the one that has least laxity, least the slack time. So basically start executing emergency tasks, the ones that have really short slacks. So at any point in time, you sort your jobs based on their slack, and you give it to the one with shorter slack. Now, as you can see, a slack of each task changes over time, right? If my slack now is L, my slack, and if I don't execute, if I don't run, my slack at time t plus 1 is L minus 1. If I do run, then my slack doesn't change. Time t plus 1, I have executed 1, and I am 1 unit closer to my deadline. So they cancel out. My slack doesn't change. So this notion of a slack for each job changes over time based on whether or not they got scheduled. Because the slack is changing and because we're sorting based on slack, then each job gets a new priority every time unit. Could get a new priority if their slack changes or if anybody else's slack changes. As a result, this is fully dynamic scheduling policy because we're just changing jobs priorities over time. Yeah, so the job with the smallest laxity has the highest priority in the system. Now there is another interesting theorem that again we're not going to prove. You're going to just take it, and that says LLF similar to EDF is optimal with regard to all online schedulers. So basically LLF and EDF are top students in the class of online schedulers. So both of them have similar powers when it comes to scheduling, when producing feasible schedules. The problem with LLF, however, is that it's very similar to shortest remaining task first scheduling because it's kind of like impractical to implement it. I guess the reason different with the shortest remaining task first, the reason that it was impractical was because we couldn't foresee future. But here LLF is, although it is optimal, it's impractical because of this. Let's look at it. Because laxity is changing every second, right? Every whatever your smallest time unit is. And you don't want to, let's say you have two tasks with the same slack. Let's say I guess here is the example, right? I have T2 and T3. The deadline for T2 is 5, or the period, and the period of task 3 is 6. If you look at the slack of T2 is 3. A slack of T3 is also 3. So both of them have the same slack. So what do? Maybe we just randomly pick one of them. Maybe we just, so at this time, as you can see, it's probably very small, but hopefully you can read. So L1 and L2, this is laxity of task 1, laxity of task 2. Both of them have laxity 3. So they're equal. So I pick one of them and I run for a little bit. Now the other one now has lower laxity. I have to switch to the other one. Then now they're equal. I randomly, let's say, pick T2. Then immediately T3 becomes the one with lowest laxity. I have to run T3. And this actually continues, right? I have to just keep switching between the two because they're equal. I run this one, this other one becomes the lowest, then I run this one, now they're again equal. I run this one, this becomes the lowest, I have to run it. Now again, they're equal. So it's kind of like I have to context switch between the two so many times. And that's pretty bad. If you have, non-zero overhead, context switching overhead, then this is terrible, right? Okay. Now, just to put all these three scheduling policies together, we talked about rate monotonic. It's simple. Implementing it is very simple. The downside is the bound is low, right? It's close to 70%, but it's very simple. And in terms of implementation, it's really good and easy to implement. Then we have earliest deadline first. It achieves full processor utilization. It can utilize all the way to 100%. It has some misbehavior if you have an overloaded system. Then we had the least laxity first. It again could also achieve full processor utilization, but it also misbehaves if you have tasks with equal laxity. By the way, in all of the examples that I just showed you, we assume that there is 0 context switching time, right? The moment you introduce context switching overhead, then you have to go and modify all the bounds and all the schedulability tests that I introduced, because they assume that you have 0 context switching time. Okay. Now let's start talking about other types of tasks in our system. What happens if I have because again, so far all the 3 scheduling policies that I talked to you about, we're assuming that you have periodic tasks. We defined them for periodic tasks. Now, what if in my system I also have aperiodic tasks? What can I do? What are my options? So one option is, well, the moment you get an aperiodic task, just run it. Immediately get rid of it, right? The moment you get an aperiodic task, just run it. Now, this gives a fantastic response time to your aperiodic tasks, because the moment they come, you're going to run them. But it would be super bad for periodic tasks, because it would just mess up all the bounds that we talked about and all the guarantees that we had in our system. So they all go out of the door if you want to just give high priority to aperiodic tasks. Another alternative to this one is to do vice versa. So just don't do any aperiodic task unless you don't have any periodic tasks left. So basically put them in 2 different classes, dedicate your system to periodic tasks first, and once they're done, then move on to aperiodic. That is now, it gives perfect predictability for your periodic tasks. You still can use all those bounds and guarantees that you had, but it's really bad for your periodic tasks. You're just, you could potentially starve them. A better idea that last term we asked the students to implement it in lab 5. This time I'm not sure if I'm going to do that. You're lucky. Is an idea of periodic servers. So what's the idea? The idea is very similar to what I talked to you about, how we could handle interrupts. If you remember in the previous lecture on Tuesday, no, when was it? Today is Tuesday. On Thursday. So I talked about option 3 of interrupt handling, if you remember, was when you have an interrupt, create another task and give that task to the scheduler to schedule. So here is similar idea. So what's going to happen is we're going to take our periodic task and then we're going to just tweak them a little bit and make periodic tasks out of them and just introduce them to the scheduler that knows how to deal with periodic tasks, right? So we just convert them somehow in one way or another. It will depend on how we do it. There are different types of doing this transformation, but just transfer your aperiodic tasks to periodic tasks, and then now your scheduler knows how to deal with periodic tasks, so it will just deal with it itself. So that's the idea. We're going to actually, so the theme of this, it's called actually periodic servers. Now there are different types of periodic servers. I'm going to show you a couple of them. But most of them, the theme is that your server, which is the converter, right? It's the one that, as an input, gets these aperiodic tasks, and as an output produces these periodic tasks, or becomes itself the periodic task, if you wish, has a period, obviously, and has a budget. So you can think of this budget as its maximum execution time. Because we have aperiodic tasks coming, well, we're not sure if we're going to stick to this maximum execution time, but we still are going to give it a budget of B. We call it PS and BS. So the period of periodic server and the budget of periodic server. Okay, now the idea is basically what I just said. So you're going to put this periodic server here. Your aperiodic tasks, instead of putting them in your ready queue, you put them in the queue for this server, and then this server just takes them and acts as a periodic task to the scheduler. So it's kind of like a proxy. This server acts as a periodic task, so the scheduler will schedule it the way it schedules other tasks. And hopefully that means that you're going to run your aperiodic tasks alongside your periodic tasks. So that's the general idea. Again, it has different implementations. Let's look at some of those. Okay, so the first one that we're going to see is called polling server. How does it work? Well, periodic tasks and the periodic server, both of them, are going to be scheduled based on RM. So with polling server, the scheduling policy is rate monotonic. So we'll see another instance where we use EDF, but with polling server, we're going to use RM. Then the aperiodic tasks are going to arrive, and they will be queued by the PS, very similar to what we saw in the previous example, the previous picture in the previous slide. Now, this periodic server has a period, right? So it gets a priority, like any other periodic task in this system. So based on its priority, it will be scheduled at some point, right? It would be its turn. Now, if you really want to, this is where you get flexibility. So if you want to give aperiodic tasks the highest priority, you want to run them as fast as possible, then you can reduce the priority of PS, because the shorter your period is, the higher your priority becomes under RM, because we're using RM. So by playing with the period of PS, we can set sort of the priority that we're going to give to aperiodic tasks, because this PS is going to represent all those aperiodic tasks. So if we give PS a long period, it means that we are giving aperiodic tasks low priority. If we give PS short period, it means that we're going to give high priority to aperiodic tasks. And anything in between, you can just play with it. So I guess the best way to see this is through an example. So let's say we have one task in the system with period 4 and runtime of 2. And then you have a periodic server with period 5. So it's not going to get higher priority than T1. So it's going to have lower priority. And the budget is 2. So this is the budget that I talked about, which is the worst, worst case execution time. Now, let's say that these are the times that aperiodic tasks come in my system, right? So they're just going to come randomly, and they're going to last for some number of time units, and then they're going to go. So let's say I know that in hindsight. Let's say I have that. Now let's run this system and see how it works. So T1 has a shorter period, it gets higher priority, so it runs first. Now at this point, at time 2, PS gets scheduled. Now it has 2 tasks in the queue, so it can run those 2 tasks here because it gets scheduled. The moment PS runs out of tasks, so if you don't have any other tasks in your queue, the priority schedule, the PS empties its budget. So it says, okay, I'm done. I'm done with this round, with this period. I'm done. So the budget goes to 0. Then at this time, we're not going to do anything. There is no task in our system. Now here comes this one, this period. T1 again gets scheduled. At this time, a new PS job is created with budget 2. Now, at this time, this PS task or PS job gets scheduled. It looks at its queue. There is no aperiodic task in the queue, so it just goes from budget 2 to budget 0. It says I don't have any tasks, so I'm done with this period. So basically the task dies, if you wish, or the job dies. So with this period, I have no other PS job. Next period of T1 runs. At this point, we create another job for PS, again with budget of 2. Now all these 3 aperiodic tasks are queued. Now I can run them, right? At this point, I run them. And at this point, I'm done. So my budget goes to 0. Please note that this is actually less than my budget, right? I still had some time left, but because I didn't have any job in my system, I just yielded. It's kind of I yield. So I'm done with this period. And then in future, I'm gonna get some job here, some aperiodic task, but because I'm done, this is gonna go to my queue for the next period, and so on and so forth. Now, as you can see, this is kind of like inefficient because here this aperiodic task came within the time that I could have ran it. I could have executed it, right? But because I basically my budget went from whatever it was to 0, I don't have any budget, so it will have to wait for the next period. So if you look at my budget, the budget of PS gets refilled at every period. And as long as I have tasks, I execute them and my budget decreases. The moment I don't have any task, my budget goes to 0, exactly 0. And then I will wait for the next round. Again, at this time, I'm scheduled, but because I don't have any tasks, my budget goes from 2 to 0 immediately. And then again, here, my budget is refilled. I run. I don't have any tasks. My budget goes to 0. And that's basically why I can't run these 2. I got a question. So does this mean each aperiodic task is guaranteed to complete in 1 period? Not necessarily, as you can see, right? So this one came in this period, but it wasn't guaranteed to schedule in this period because of what happened here. So it was scheduled in the next period. Now, if I get a lot of tasks, then my PS can only have a certain budget. So if the budget reaches 0 and I still have tasks, then those tasks would go for the next period, right? So the PS can only run as long as it has budget. The budget gets 0, I can't run anymore. Okay, so to deal with this particular issue that we saw, a proposal is to change polling servers to deferrable servers. And the idea is everything is almost the same as polling server. We only change one thing. We say we don't yield, or I mean, we do yield, but we don't make our budget to go to 0. So we basically kind of like pause or block. If there is no tasks, then we kind of block. Very similar to your mailboxes. If you don't have any mail, then you block. And the moment you get a mail, you come back to life. You get unblocked. It's very similar. So as long as you have budget, you start running. If you don't have any tasks, then you don't make your budget go to 0 and die. You just get blocked. You preserve your budget. And here is an example, the same example we saw in the previous one. So nothing happens here so far. Here, at this point, I was scheduled, the PS is scheduled, but because it doesn't have any tasks, it just blocks. It doesn't die. It doesn't exit. So the moment it gets a task here, it comes back to life and it schedules it. Now, in this period, we still are not dead. We still have budget. So you might ask, why am I not running these two? The reason I cannot run these two is because T1 comes here. So T1 has higher scheduling higher priority because it has a shorter period. So although if there was no T1, I could have actually ran these two as well, because at the end of this, I get blocked again, but I preserve my budget. And then here I get them. So I would want to wake up and run them, get unblocked and run them, but T1 has higher priority. So T1 runs. So I will have to run these two at this point. Then again, I get blocked. And then I receive this aperiodic task and I get unblocked, I run it. And again happens that this T1 has higher priority and so on and so forth. So in this example, if I look at the budget again gets refilled every period. As I run tasks, my budget goes down, but if I don't, I preserve my budget. Now, in this one, I'm not using it, so it gets refilled again. I use it here. Again, I cannot use it. Although I have a budget here, I cannot run them. Now it gets refilled. I use some of it. I keep it. I use it. And I keep it. So that's basically the idea of deferrable servers. But again, as you saw, these cannot run. If you wanted to run these two, you should have given your polling server or deferrable or your DC a lower a shorter period, and that would have made it higher priority, and that would have allowed you to run these two. Okay. Now this is the last priority server idea I'm going to throw out. So far we've seen two, polling server and deferrable server. And now this is the total bandwidth server. It's a little bit more involved. The first two use RM. This one uses EDF. So the main scheduling policy is EDF. Now we're going to, as I said, turn aperiodic tasks somehow to periodic tasks. How we did it in polling server and deferrable server was making the server act as a periodic task. So run on behalf of those. Now, in this one, we're going to actually turn our aperiodic task. We're going to manually or artificially assign periods to our tasks. See, when you're doing EDF, all EDF cares about is your deadline. So if EDF knows your deadline, it can schedule you. It can give you assign you a priority. Now, the problem with aperiodic tasks is they don't have period. So how do we solve it? Well, we artificially assign period to our tasks. And by doing so, we make them, you know, a normal task for EDF to schedule. Now, here comes the tricky part. How do we assign deadlines? And I think this is the beauty of this total bandwidth server. So with EDF, you know that your system is schedulable if total utilization is less than 100%. Now, you know your periodic tasks. You can calculate your total utilization for periodic tasks. That gives you some leeway. So let's say the total is 70%. Now you have 30% left. So as long as you can make these new aperiodic tasks, not because when you assign deadlines to your tasks, you're sort of defining utilization for them, right? It's a synthetic utilization because they're not going to come every time. It's going to be just one time thing, and they schedule and they go. But the way you assign deadline to them will set their utilization, because utilization, if you remember, was execution time divided by period, which in EDF case is basically your deadline, right? Now, the further your deadline is, the lower your utilization is, right? Because the deadline is in the denominator. So the idea with total bandwidth server is to set the highest possible deadline for our aperiodic tasks such that we don't overload the system. So in essence, what do we want? So aperiodic tasks, we're going to artificially assign them deadline. But again, the trick here is that we don't want the utilization to exceed. So in the worst case, we don't want it to exceed, let's say, you know, the 100%. But let's say in the example I said, you know that for your periodic tasks, you have 70%. Now there is the 30% left of utilization. So this becomes your UTB. So you want all your aperiodic tasks to collectively use this 30%. So this 30% becomes your bandwidth, basically, for your aperiodic tasks, because you cannot go further than this, because your periodic tasks are using 70% of utilization. Now, if aperiodic tasks have utilization of more than 30%, then the system is not schedulable, because the total utilization goes up above 1, which is not desirable. Oh my God, I'm over time so much. I kept going. So sorry. Okay, so I guess I'm gonna stop here. So sorry. I lost track of time and nobody messaged me. Anyways, I'm gonna stop here. We'll continue this in the next lecture. Thank you so much for those who attended the lecture, and for those of you who are going to watch. I'm so sorry for the beginning that I spent about 10 minutes with a failed experiment. So take care, stay healthy, and talk to you later. Bye-bye.